right. Okay. Okay. Solid state processes. So after spending quite a bit of time discussing arc welding processes, now we're flying through other processes that are less used in our province, but that are very important, and I would like you to have an awareness. So we went from melting the base metal using the energy of an arc to melting the base metal using the energy of a laser or an electron beam, to melting the base metal using the energy of electric resistance, to now not melting the base metal. Completely different thing. In many aspects, there are similarities. Some parts will be hot, some parts will be cold. But the dissimilarity of melting versus not melting is enormous. And the key thing here is that when you melt something, goes back to solid with a microstructure that has dendrites and might have like a solidification shrinkage and porosity and segregation and many problems. In solid state, we have none of those problems. We can have other problems, but we don't have those. In addition, in solid state processes, because they're often based on high deformation, the grain size can be small. So funny enough, in solid state processes, the welding, the joining process sometimes ends up with material better than what we had before. And that's quite cool. Let's see. I would like to start with friction stir welding. Friction stir welding, I mentioned to you in our first class and friction stir welding is the method that is used to weld the tanks of most rockets today. Friction stir welding is of the mainstream welding processes is the newest, was invented in the 80s. And had, like, for some applications, had quite a bit fast and deep uptake. So you're not likely to see friction stir welding around. Arc welding is so much more in amount of welds being done. But for some things, friction stir welding is the name of the game. The reason friction stir welding is used for the bodies of rockets is because some bright minds realized that if they mix the aluminum alloy of the tanks with lithium, lithium is very light, and you end up with a tank that is lighter and maintain the strength. So all the weight you saved in the tank, now you can put it in your payload with the same rocket as before. That's genius. What's the problem? Well, the problem is you cannot weld it. It had lots of problems of hot cracking and lots of problems during the solidification of those welds. The problem was originally solved by a Canadian company using plasma welding. And the first tanks of the space shuttle were welded with plasma, with variable polarity plasma. Quite an expensive process. Eventually, people figure out, okay, we can try this new process that is in solid state, so we don't have solidification processes problems anymore. And they move into friction stir welding. It is so widespread, right, that SpaceX and Blue Origin both use the friction stir welding for the body of their rockets. And if you read Elon Musk's biography, there is a whole page devoted to how Blue Origin stole the friction stir welding engineer from SpaceX, and Elon Musk was not pleased. And then you have a battle of the titans, right? Who's the billionaire who can hold a bigger grudge? So, one last thing, body rockets or some aerospace components in China are still welded with variable polarity plasma arc welding. Interesting, although they have plenty of friction stir welding too. How does friction stir welding work? The first time somebody described this to me, I didn't believe it, but it's true, and please believe me. The original process used a milling machine, and instead of cutting and chipping away the metal, you have this tool that is rotating. This part here is a circular tool that is rotating, and the tip has what is called a tool that originally used to be a metric size thread. Just like that, that's it, metric size thread. And this spins, and once it reaches steady state, what happens is amazing. The frictional heating softens the metal. Because the metal is softer, then it's easier to deform and to move left to right, right to left, and that way I erase mechanically my interface. And this deformation of the metal causes heat. And this heat is what makes the metal softer. So we have a localized heating and coupled heating and plastic deformation around the pin here in the tool. And there is no melting. You can reach melting if you overcook the part, but then you ruin it. That gives you the effects. So when you do it right, there is no melting. The original patent mentions no melting. And by the time this is done, you end up with a microstructure with a very fine grain size, really good mechanical properties, and no solidification defects. What else would you want, right? The pin also has a shoulder because when the material is so hot and so soft, it wants to squirt out. So on one hand, you have what they call an anvil, that is a very stiff piece of steel, say, that prevents the this piece of steel prevents the hot metal from going out, and also prevents it from going out through the top. If we look at it from the top, here we see the shoulder, we see the pin, and the surface marks that are left by the shoulder. If we do a front view, like kind of a cross section, we see our cylindrical tool, we see the cylindrical pin with the metric thread, although there are many other configurations too. And we have now two things. We have a heat affected zone because everything that gets hot will eventually give us a heat affected zone. But we have something else that is called the thermomechanically affected zone, because now that was not only hot, but was also very deformed by all the action of the pin. Very interesting. So in this case, there's no melt to protect. That's the story of solid state processes. No need for gases, no need for fluxes. Everybody's happy. Filler material. Typically, friction stir welding is done autogenously. And that's okay, because since we don't melt the metal, we don't need to worry that when it solidifies again, it's gonna be ugly. There have been experiments with consumables, but for us and for 90% or 99% of all friction stir welding, this is, the pin is non-consumable and the weld is autogenous. And in this case, you have a mechanical motion that is rotation and translation. The pin, the tool is rotating around this axis, and it's also translating and making the weld. Here you get to see the weld nugget, the heat affected zone that is not deformed, and then the thermomechanically affected zone in which there was intensive formation. The weld nugget is like where the pin was, and there is even much higher deformation. And the reason this looks asymmetric, typically a cross section of an arc weld is symmetric, not asymmetric. The reason is asymmetric in this case is because as we move in one direction, the pin rotates, and one side of the pin is going to be moving fast in the same direction of the tool, and the other is going to be retreating, going away. This is called the retreating side. In this case, if the weld was moving into the screen, the right side was spinning into us, and the left side was spinning into the screen, even faster than the travel speed. This is so interesting. Okay, characteristic. Works best with low melting temperature alloys, like aluminum and magnesium. And of course, because the pin is not meant to be melted and has to maintain structural integrity. So I can use a steel pin to do aluminum. But what do I use to make steel? Right? What material can be so strong at high temperatures? And there are some. There are ceramics, people try tungsten, but the bottom line is for aluminum, this works awesome, and for steel, it's not mainstream yet. Actually, steel is so easy to weld by arc that why worry, right? But people are trying. People are trying. I believe there will be success, and I believe there will eventually be applications. But for the most part, friction stir welding is aluminum and magnesium. This can weld unweldable alloys because we have no solidification problems. We have no hydrogen problems. It can weld dissimilar alloys because if I try to weld, say, two very different alloys and I melt them, when they solidify, typically they will recombine in the form of intermetallics. And intermetallics are very brittle, and our toughness is nearly zero. But in this case, because I'm not melting and I'm not resolidifying, the amount of intermetallics present is much smaller. So we have a much better chance. Some people are even trying this for welding steel to aluminum, which is kind of the holy grail of joining. Yeah, it works kind of okay in some cases. But there are many combinations of materials that you cannot do with fusion, and yes, you can do with friction stir welding. No problem out of position. You want flat position, fine. You want overhead, who cares? Because being mechanical, we don't have any more the force of gravity pulling on a liquid and the force of capillarity trying to resist. No more problems of that now. The typical joint configuration here is a square butt joint with zero gap. And if there is any gap, typically it will end up becoming a porosity or being some sort of a problem, right? And that means the tolerances are very tight. So for welding with friction stir welding, we typically have to machine the joint preparation. It's not that you go and flame cut it happily as we often do with steel. Friction stir welding cannot be done manually. And the reason is there are enormous forces involved. If you ever come to our lab, you're gonna see we have an enormous milling machine. That's our friction stir welding machine. And when you see it in action, you'll realize, no. This is way more intense than holding an electric drill from Home Depot, right? Because of these big forces, it requires very stiff and heavy and expensive fixtures. So the way NASA welds the rockets is by having very, very stiff and expensive fixtures to hold the metal in place as this is welded. You can imagine all these forces try to reopen the joint. So they have to be clamped very, very stiffly. You can also imagine that the start and the end of the weld is tough. How do you start it? Right? You have kind of to dig in, and then when you finish, if you pull the tool out, you're gonna leave a hole there, right? So starts and ends are difficult. You typically use run in and run out tabs. is different than arc welding, in which there are ways of starting things with elegance. Much like in all the other types of fusion welding, if I have no translation, is what we call spot welding. And in spot welding, in spot welding, you just go in and out. And if you do it properly, you accomplish fusion, even if you leave a little hole in the center. So friction stir spot welding is one of the ways that have been used in practice to weld steel to aluminum in cars. Applications. Shop welding, you're not going to be doing friction stir welding in the field. You use it for full penetration or two-side penetration butt joints in aluminum for rocket bodies, but other things. Ship decks, trains. I don't know if you know, but one of the latest generations of ships, the combat ships in the US is called the literal combat ship, that is meant to be somewhere near shore. And that's aluminum, and that's welded with friction stir welding. And one of the engineers who was associated leading this welding, I got a big award for her job in doing these ships. Let me show you a video of friction stir welding in action. So the SME videos, Society of Manufacturing Engineering videos I have, are so old that this didn't exist yet. So this video comes from elsewhere. So you just saw the start of the weld is what they call the plunge. The tool went in, is going in, and now the shoulder is touching the plate, but doesn't dig into the plate. And they started the translation now. I believe this video, I don't know where it is from. You see there's a little bit of a flash here on the side. Is that cool? Now, this was the welding of two aluminum plates. Often when we have the class in the lab, we run a friction stir welding demo too. We have so many toys there, and soon enough, we're gonna be running laser demos. Please come to the lab after the class or after COVID. So let me show you a video, which I believe is from Oak Ridge National Lab, in which they are trying to weld pipe with friction stir welding. So those of you who have experienced welding pipe, you're gonna appreciate the promise this holds. Of course, the challenges are big, and this is not something that is mainstream. So this is a lab demo, but look at how cool it is. So this inner cylinder is what is going to be the anvil and reacting against the pressure of the tool. See, this is pressing against the pipe. So far, it doesn't look all that different than an orbital welder, but look at the detail now. There's a weld in steel, single pass, full penetration. Check it out. It's red hot. Often the tools used for steel are proprietary, because they have to keep strength even when they are red hot. Now they're finishing it, and they're going to run over the start of the weld. So they're going to erase whatever mess they made, and they just put a run out tab. This looks like space age, doesn't it? All right, there you go. So they say nothing about the tests, and in the pipeline industry, doesn't matter how how beautiful the weld is or how beautiful the grinding is, you have to test it and see how it goes. Knowing how difficult those tests are, I doubt that this is a ready product. And in addition, the tests are very much tailored for arc welding. So even if these were to perform well, it would be hard to qualify. I want to ask you a question. What temperature do you think the weld is? We know it's below melting. Anybody wants to guess some temperature of operation? Yeah, I like the 800C. I like the 600C, not so much. Okay, you guys are awesome. Okay, liquidus temperature for sure not, because at liquidus you reach full liquid, right? So it would not be. Yeah, you guys are super awesome. Yeah, this thing of teaching online is not that bad after all. So let me expand my my window so I see everybody's comments here. Wow. Exactly. Okay, so you guys got it. Let me comment on something. For sure, it's not liquidus, because a liquidus means you reach 100% melting, and this should reach 0% melting. If you had said solidus instead of liquidus, I would have said maybe, but it's super dangerous. Typically, we are trying to be well below liquidus. And somebody suggested above austenization. Absolutely. About 727, assuming this is like carbon, iron carbon binary. Exactly, it has to be above that. And the reason is that in iron, the austenite is so much softer, exactly, because it's an FCC instead of being a BCC, austenite is so much softer, and you want to reach austenization. I like the comments of the color. Yes, when the color is red, it means you're above 600 degrees, typically quite a bit above, but you need to be more than 600 degrees. You want to be above austenization. Yes, so the temperature there, I don't know, but for sure it's outside 27. I would say that temperature, judging by that red, would be of the order of 800 C, right? Because hotter than that looks white hot. Super interesting, super interesting. So, but now there is a problem, because if they austenized, that means that during cooling is going to transform. And the heat input there, I don't know what it is, but if it cools too fast, you might end up with too hard a microstructure, right? There might be issues of heat input to worry about there. Okay, awesome, super awesome. I want to teach you a third solid state process called friction welding. Friction welding is used to make landing gears in planes, or to put together the shafts of turbines, of jet turbines, and many other things. And this, like everything, mechanical energy is much more expensive than electrical energy. So these things tend to require like relatively heavy and expensive capital equipment. So how does it work? In this case, you get, let's start with the one that is friction welding, that rotating friction welding. So the section is circular, and you hold one firm, and the other is rotating. It can be rotating because you're driving it with some sort of a transmission, or can be rotating because it has a huge flywheel and you give it enough inertia that is rotating. Then you, in the second step, you put the two together and you put some amount of pressure. Now that friction there, one is rotating and the other is not, is going to generate a lot of heat. And that lot of heat is not meant to melt like everything we have talked so far. Always below the solidus, always below the solidus, and often always below the minimum eutectic of the material system, because sometimes you might have some like low melting points that you didn't mean to have, but you can. And this localized heating creates localized softening. And as you put pressure, they form what it's called an upset, and starts kind of to bring out some amount of the material, like it forms some sort of a scarf or a lip, right? And at some point you stop the motion. If it is driven by a transmission, you stop the transmission, and if it is driven by inertia, it just will eventually run out of inertia. And the joints you get with this process tend to be very, very, very good quality. Now, you're limited to circular sections in this case. This is autogenous. People have tried friction surfacing, which is such, I don't even know if it is commercial, right? But the way essentially is like it's like chalk, right? You go with chalk over the sidewalk or on a board, and the chalk wears out and it's all on the board or all in the sidewalk. It's a similar thing, of course, but using this plastic deformation at high temperature. But in any case, friction welding is autogenous. Can be driven by a transmission, a direct drive welding, or can be by inertia. Now, something that is much newer is, how about if having a rotating motion that confines us to circular shapes? We have a reciprocating motion that enables us to have pretty much any other geometry, squares, for example, or we can weld blades of a jet engine onto the disc and make what is called a blisk. That's common in jet fighters, because the attachment of the blade to the disc in a passenger plane typically has something that looks like a Christmas tree for mechanical locking. But all that is wasted space and wasted weight. So if you make it all in one part, it's going to be super expensive, but it's going to be much lighter and much more compact. So characteristics. Friction welding works well with most alloys. There's a repeating story with solid state processes in which it can weld the unweldable processes. It's restricted to simple geometries. Circular sections for friction welding and flat surfaces for linear friction welding cannot be done manually, same as usual, because the forces are too high. Stiff, heavy equipment. In this case, there is no tool. The applications are shop welding and things that much of this is aerospace. An interesting thing, long ago, I wrote a paper on welding processes for aeronautics. And then is when I first heard about linear friction welding for making blisks, but it was just at the edge. So nobody was very forthcoming on what they were doing. Now it's pretty mainstream and it's well known, but people were telling me like half-truths all over the place. And I knew that something was coming, although I didn't know exactly how, but it's very interesting, very interesting. Let me show you a video about friction welding.
In solid-state welding, coalescence is created at temperatures less than the melting temperature of the base metals with pressure. The two most used solid-state welding processes are friction welding and ultrasonic welding. Friction welding is an extremely rapid method of welding workpieces, typically in butt joints, by frictional heat and axial force. Frictional heat is generated by rapidly rotating a workpiece against a stationary workpiece until the interfacing or faying surfaces reach the proper temperature. The weld is completed by an upsetting operation which consists of the rapid application of additional axial force as or just after the rotation stops. This upsetting operation forces hot metal, oxides, and impurities out of the joint. In general, one workpiece must have an axis of symmetry and be capable of being rotated about that axis. Workpieces are usually either in butt or T-joints, with the pieces being bar to bar, bar to tube, tube to tube, and bar or tube to plate or disc. Additionally, friction welding can be used to join a wide range of similar and dissimilar materials, including most metals and alloys, some metal matrix composites, ceramics, and plastics. Ultrasonic welding is a method of producing lap joints by high-frequency vibratory energy and moderate force. This induces interatomic attraction.
In a second, I'll talk about that later. So you got to see how it generates the heat and how it starts to generate this lip. I was just trying to be too smart, I guess, about this. Let's go. Sparks that happen at the beginning, that's part of the cool thing of friction welding. Those sparks took away all the impurities, everything that could be wrong goes away. We don't need to do much cleaning for friction welding. You also saw how the motion was stopped all of a sudden. That means this was a direct drive friction system. When we talk about the formulas for calculating temperatures and phenomena in welding, those can be applied to these processes too. And some things that we're not going to discuss in this class, those who took the heat transfer class with me last term will recognize very quickly how our analysis of semi-infinite solid and other types of calculations we did in the heat transfer class would apply to calculate what thing gets how hot during this process. What I want to show you here is about linear friction welding, right? The type of thing that was so hush-hush when I was writing my paper. Here you have a turbine in a passenger jet, and I'm sure this has a proper name, this kind of super dove tail joints. But here's a blade. This is what is called a disc. And here you have the joint area that is heavy and taking space. This is for a jet fighter. Look, this is what they call the blisk, because it's a mixture of blade and disc. The blades are directly welded to the disc. How you do it? Well, I don't have videos of that because they still don't want you to have that. But I have videos of other type of linear friction welding that you're gonna see is more or less the same. Here we go.
Low-cost linear friction welding is an area TWI has been interested in for some time under the LinFric project. Linear friction welding is ideal for joining blades to discs in turbine manufacture. They're called blisks. And these are some images of welds made on the new LinFric machine here at Abington. Well, successful welds were achieved in a variety of section combinations. The linear friction team also examined the process with titanium specimens.
Well, no offense to the Brits in the class, but I still like better my accent. Ultrasonic, you saw how it works, and now the difficulty with linear friction welding is you need a lot of stiffness, and you're moving big masses at a high frequency. It's not going to be easy. Ultrasonic welding is another solid state process, and to some extent is not that different from linear friction welding. The difference is things are done now at the ultrasonic frequency. So instead of moving the whole part, as we saw it before in this previous video, instead of moving the parts relative to each other, you don't move the parts, but you impart shock waves through a sound transducer that cause this localized motion at the interface. And guess what? You're a big user of it, because that's the way you weld the bottom of the toothpaste tubes. So next time when you go brush your teeth tonight, check it out. That is ultrasonic welding. That is autogenous. It's even good for additive manufacturing because you can make layer over layer by moving the transducer over the layers and having the joining happen at the interface. So very similar to linear friction welding, but also very different in that we don't move the parts, we just impart shock waves. Frequencies are beyond human hearing. I have a question here about the linear friction welding that asks, how do we clean things afterwards? Yes, in friction welding or linear, it's not filing, you machine it. Those parts are machined afterwards. This machining, what do you do? Not grinding. Okay, so the amplitude of the movements are small, but the equipment is relatively expensive. Again, this you justify when you need to weld like 50 million toothpaste tubes, not when you need to weld one. What you weld with this is thermoplastics. You can do additive manufacturing. I'm not very familiar with the ASME code, but I learned that the latest version of the ASME code now, ASME 9, accounts for the welding of polymers, this is one of the examples. So let's see if here I have video of ultrasonic welding.
It's ceramics and plastics. Composite. Additionally, friction welding can be used to join a wide range of similar and dissimilar materials, including most metals and alloys, some metal matrix composites, ceramics, and plastics. Ultrasonic welding is a method of producing lap joints by high-frequency vibratory energy and moderate force. This induces interatomic attraction and metallurgical bonding at the weld interface surfaces with relatively little heat. The workpieces are clamped between two welding tips called sonotrodes or jaws. Vibratory energy is conducted through one or both tips, which oscillate laterally as a perpendicular force ensures contact of the workpieces. The oscillating action disrupts the interface surface films and permits metal-to-metal contact.
This video is exaggerating the lateral motion. Actually, the lateral motion is nothing like that. It's much, much more smaller, and you don't get to see it.
This creates plastic deformation at the interface, resulting in a solid metallurgical bond. Under proper conditions, interface temperatures reach only 35 to 50% of the workpiece melting temperature. Basic equipment includes an electric power supply, a frequency converter to increase line frequency to generally 15,000 to 75,000 hertz, one or more transducers to convert that power into acoustical power of the same frequency, a coupling system to transmit the acoustical power to the welding tip and into the workpieces, a workpiece support system, and a force application system. Ultrasonic welding typically requires at least one of the workpieces to be thin. The usual welds are spot welds and straight or circular seam welds. Workpiece distortion is limited. Ductile metals in similar or dissimilar combinations are ideal workpieces, although hard metals also can be welded. Filler metals are not normally required, although they can assist in joining difficult to weld dissimilar metals. The electrical and electronics industries are the principal users of ultrasonic welding. Limited applications are also found in the automobile, nuclear, and aerospace industries.
Oh, they forgot to say toothpaste industry. So one more solid state process, explosive welding, explosion welding. This welding process was not invented, but was discovered. After World War I, people found that some of the shells that had hit the armor were stuck to the armor. And somebody, and I don't know who, and if I was anywhere near shells hitting armor, I would probably have too much PTSD. But they wondered, why is this stuck? And they looked at it in the microscope. And what did they see? They saw that the interface between the shell and the armor had this wavy pattern. And this wavy pattern is causing, at the very least, mechanical interlocking, but also because of the high heat and the high deformation and the surface gets cleaned out quite well, right? And of course, people understood it, and now we use it commercially to make claddings. For example, if you have a chemical reactor in which you want to have a titanium surface, titanium is super expensive. So you might as well have a steel vessel that has a titanium surface. Now, how do you make a titanium surface over a steel? There are many ways, all very expensive, but one of the least expensive is you put your steel plate, you put your titanium plate on top, you put explosive charges, and you detonate it. And the detonation drives the titanium clad, what they call the flyer, onto the base metal. And as they have all, you only hear boom, but they have this very well understood, and everything is very well calibrated and timed, such as the front of the explosion is moving and you're burning the explosive, you're pushing the plate, the clad, what is called the flyer, against the base component, and and you start forming this pattern. This happens nearly instantly, right? And you have shock waves. So in this case, you have pressures that are higher than plasticity, but they are localized, right? And other thing that happens is as the flyer is being pushed against the base plate, it creates a jet that expels impurities. And this process is not very well understood, but there is something cool. There are some theories that say you have a jet of molten metal coming out here. To some extent, is a similar effect to what you have in shaped charges that are made actually to penetrate armor, in which the shape of the charge is like a hollow cone. And when it hits, all the force gets concentrated at the very vertex of this hollow cone and spits molten metal. And this is one of the theories of what's happening here, right? Depending on the velocity of propagation of your explosion, you can have different interface patterns. And here it's 1800 meters per second. This is fast, right? It's much faster than the speed of sound in air, but it starts to become comparable with the speed of sound in the metal, right? As it's faster, you create all these deformations. There is a very similar process that is called magnetic pulse welding, which is for smaller components and is made in the automotive industry, in which you use electromagnetic forces to push the flyer against the base material, and you end up with very, very similar results. A very, very interesting process. So in this case, the filler metal is the clad plate. This is not so much for joining as for like cladding, and the mechanical motion then is pressing against the interface. Can join large areas. So you go boom, and all of a sudden you welded, I don't know, 10 square feet or more. Much more than 10 square feet of metal, 100 square feet of metal. If you have to do that with cladding, with either lasers or sub-arc, it would take forever, and you can have the defects of solidification. Explosive welding can join dissimilar materials because there is no fusion, there is no melting, so you have very few intermetallics, very few. And in addition, you have this pattern in the interface that creates mechanical interlocking. You're not going to be doing it in your backyard. You need special permissions. People tend to do it inside mines. So the explosion is confined under a mountain. I need very special permits to do this. And now when you talk about welding parameters, you don't talk anymore about like current and voltage, but you talk about what explosive you're using and how you're igniting it. Another somewhat similar solid state process is called roll welding. And you might have it at your house. This is the way you combine copper with steel when you make cooking pots, right? The copper will help distribute the heat to the bottom of the pot, but the pot is mostly done out of steel, right? And this is the way it is. You roll them, and the heat and the pressure and the mechanical, the plastic deformation creates this metallurgical bond, and you end up having this bimetallic plate. So I have 3 minutes, and in those 3 minutes, I want to show you very quickly a really cool process based on